Our fourth plenary presentation is given by Dr. Albert Theuwissen of Harvest Imaging. He will talk on "There's more to the picture than meets the eye." Let me briefly introduce Dr. Albert Theuwissen. Dr. Albert Theuwissen is part-time professor at Delft University of Technology, Netherlands, and founder CEO of Harvest Imaging, Belgium. He is president and co-founder of the International Image Sensor Society, a non-profit Californian-based organization. Albert got his MSc and PhD from the KU Leuven, Belgium, worked for Philips and Dalsa. He has over 240 publications and more than 25 patents. Harvest Imaging provides training in the field of digital imaging. Albert has conducted 240 plus trainings for 3,500 plus participants worldwide. He can be seen as a training entrepreneur or an entrepreneurial trainer. He was ISSCC 2010 ITPC chair and a distinguished lecturer for IEEE EDS and SSCS. Please join me in welcoming Dr. Albert Theuwissen.
Good morning, good afternoon, or maybe good evening, depending on where you are on the globe. I would like to take this opportunity to thank the organizing committee for inviting me at the ISSCC 2021 to give this plenary talk entitled "There's More to the Picture Than Meets the Eye." And I added a subtitle to it: "In the future it will only become more so." Although this is going to be a technical talk, technical presentation, I would like to start with some business information and a market overview of the CMOS image sensor market. On the horizontal axis in this graph over here, we have the time, the year. On the left axis over here, we have the worldwide turnover in billions of dollars. And on the right side, we have the worldwide turnover in shipment units. And what you can see, it's listed at the bottom of the sheet that from the year 2019 to the year 2024, it's forecasted that the turnover is going to increase almost by a factor of 2. So that is actually good news. But I would like to draw your attention to two small details in this graph. And the first one is the growth of the CMOS image sensor market in the year 2019. In that year 2019, CMOS image sensor market was the only growing segment within the total semiconductor business that had a positive growth. And there's another interesting point over here, and that is the year 2020. The forecast that was made in the spring of the year 2020 was said that we would see a decrease in turnover of 4% to, I guess, well-known reasons. But actually the forecast was adjusted, and in the fall of the year 2020, it was said that there will be an increase, a positive growth of 7%. And who knows, maybe all of us contributed to all our Zoom meetings. But altogether, we can say that there's very good news for imaging engineers. There's a lot of excellent job opportunities ahead of us. Where does actually that growth in 2019, where did that came from? Well, in the first place, what we see is that we go to multiple cameras in mobile phones. Another growth market is the automotive applications. We see a lot of cameras popping up in and outside the car. And finally, also security applications are still growing. But if we look a little bit further ahead in the future, then we see that new markets will pop up, and especially virtual and augmented reality will fuel extra growth for the CMOS image sensor market, and also the Internet of Things and home appliances. And if we look a little bit further than just a couple of years, let's say if we look about 5 years ahead, then we see some new disruptive technology popping up on the horizon, being the combined CMOS image sensor with artificial intelligence. If I look to application areas, then there's a large group of applications that is trying to copy the human visual system. And examples are, for instance, digital photography or video recorders or scanners, these kind of things. But there's also a large group of applications out that is trying to surpass the human visual system. Think about high speed. There are cameras on the market that do more than 100 million frames in a second already. And metrology, we cannot do any absolute measurements with the human eye. Extended wavelength, operating conditions. For instance, we operate the human eye at 36, 37 degrees C. But CMOS image sensors, they can easily be operated at liquid nitrogen for astronomy applications, for instance. Small size, endoscopes for medical and industrial vision, and so on and so forth. Radiation hard imaging is another example where we actually surpass with our silicon devices, we surpass the human visual system. And actually, you can make a nice analogy between the human visual system and the digital image sensors in the same way as you can make an analogy between the human brain and a digital computer. There are a lot of things that you can do much better by the silicon devices compared to the human visual system. But still we can learn a lot from the human biology. And what comes to my mind is power consumption, for instance, or edge processing. Processing between pixels on the chip is very, very, very minor. While on the human eye on the retina level, there's a lot of processing taking place between the various rods and cones. I show you here a floor plan of a CMOS image sensors, and you see at the heart of this floor plan over here, the large area is occupied by pixels, by light-sensitive elements. But around these pixels, we do have a lot of periphery. Digital circuitry, analog circuitry. Digital circuitry to drive the sensor, to steer the sensor. Analog circuitry to take the signals out of the pixels. And if we talk about pixels, then actually we talk about pixel sizes of 0.7 micrometer up to 20 micrometer and even more. Even more, especially for the medical world. They work with relative large pixels. Number of pixels that can be a handful, a few thousand, but that can also millions and millions of pixels. It's mentioned over here 100 million, but in reality we go easily above the 100 million if needed by the application. And if you combine now the pixel size with the number of pixels, then actually you can easily calculate that smaller devices, they have an area of 0.5 millimeters square, while larger devices, they have just a size of 20 centimeter by 20 centimeter. We are no longer talking about millimeter square, we are talking about centimeter square. The pixels are very often covered by a color filter, especially in the case when we would like to make color images. And I show you an example over here of what is being known as a Bayer pattern, where we have for every red and every blue pixel, you see that we have 2 green pixels. And altogether, a real chip looks like the following sheet. You see in the center part, again, the large light-sensitive part, and around that light-sensitive part, we all have the periphery. On the next sheet, I show you the evolution of the pixel size of CMOS image sensors. Horizontal axis is the year, as you can see. And on the left axis, I have various parameters, including the pixel size. So all these dots over here, they represent numbers, figures that were reported in the literature. And then we have the red line that is acting as a kind of a regression line through all these data points. And you see that there's a constant decrease over the last 2-3 decades. There's a constant decrease in pixel size. So if we say that the pixel pitch, for instance, is proportional to P, then I think it's clear that the chip size is proportional to P squared, but the chip cost is also proportional to P squared, and sometimes even P to the power 3. So you see immediately that if I reduce the pixel size, if I can reduce the pixel size, I do reduce the chip cost. But on the other hand, you also have to look to the performance of the devices. And if you reduce the pixel, then unfortunately the signal is becoming smaller and the noise is becoming worse. So your signal to noise ratio is becoming proportional to P squared and is actually becoming bad, becoming worse. The same is true for dynamic range. Dynamic range is saturation over noise. Saturation is going down with smaller pixels. Noise is going up with smaller pixels. And your dynamic range is going down. So that's not really good news. Interesting actually to see is, if we look again to the curve over here, is that we have a constant drive to go to smaller pixels. And we know in the meantime that the reason behind this is the chip cost. But interesting is to see that over the years we went to different pixel architectures, different pixel configurations. In the mid-90s, so to say, we had pixels that were based on a single transistor, 1T pixel. And then we switched to active pixels with 3 transistors in a pixel, to 4 transistors in a pixel. And then the last recent technology over here is where we go to the so-called shared concept of pixels. And then you can say that on the average, the amount of transistors per pixel is less than 2. So the technology, the architecture of the pixel changed, but we constantly go to smaller pixels. And if you go to smaller pixels, then what you see is that you also need a more advanced technology node to make these pixels, to make these devices. And that is indicated over here by the green line. So for every red dot over here, you should find a green dot over here telling us what the technology node is of the CMOS technology used to make these devices. So that's on the same scale. And what you see is, again, that there's a constant drive to go to more advanced technology node, to more advanced process to fabricate these devices. And very strangely, these lines, the red regression line and the green one, they run almost in parallel. And the distance between the two is around 20 times. So the ratio of the pixel size over the technology node is a factor of 20. I added the third line over here, the blue line, and that is the so-called IRDS, the International Roadmap for Devices and Systems. And you can consider this as the most advanced technology available in the world that is being used to make DRAMs, to fabricate DRAMs. And what you see is if you compare the blue line with the green line and the horizontal direction, then there's a difference of 10 years. So the technology that is being used today in DRAM to make the most advanced DRAMs most probably will be used for CMOS image sensors in 10 years from now. And you can ask yourself, why do we have to wait 1 decade? Well, that all has to do with the fact that a technology that we have today for the DRAMs is not compatible with CMOS image sensors. And I will come back to that later on. If you go to smaller pixels, I mentioned that already, your saturation level is going down and your noise is going up. And I try to show that over here in this graph, in this picture that is artificially manipulated, so to say. I go from pixel sizes of 1 micrometer at the left over pixel sizes of, you see, decreasing pixel sizes, and finally I end up with 0.2 micrometer over here at the right side. And the amount of electrons that I can store in these pixels goes from 10,000 all the way down to 40 electrons. Well, based on this number of electrons, you can calculate the signal-to-noise ratio, and these numbers are also shown at the top left. We start off with 40 dBs, 40 dBs, which is acceptable, which is enough signal-to-noise ratio to make acceptable, nice images. And I go down all the way to the right side of 16 dBs, and you see that the noise is popping up. The noise is popping up because the amount of electrons that I can store in such a pixel is not large enough. By the way, the technology is available to make these pixels of 0.2 by 0.2 micrometer. But you see what the result is. We cannot store enough charges, and actually the signal-to-noise ratio, the dynamic range and the performance of our devices is becoming very bad. I show you here a circuit diagram of a pixel, of a typical pixel that you and I have these days in our pocket in our mobile phones. It's a pixel that is composed out of 4 transistors. Together with the 4 transistors, we have 1 photodiode over here. We have in the pixel an amplifier over here, a buffer. I will come back to that immediately. And then we have 1, 2, 3 switches. They are built up by means of an MOS transistor as well. So our pixel is just 4 N-type transistors and has 5 connects, so 5 metal connects that go into the pixel. Looks very simple, looks very easy to design these kind of pixels, but nevertheless, millions of person-hours are being spent on research and development. Why? Because these pixels are being made in such a way that they have become extremely sensitive to electrons. Photon-generated electrons, of course, that's what we are looking after. But also electrons that have generated by means of noise. They do not carry a flag telling you, hey, I am noise generated, don't collect me. No, all these pixels, they also nicely connect the noise electrons. And that actually means that for every new technology, for every new design, this pixel needs to be optimized again and again. And moreover, if you look to the processing, fabrication process, the window that is available to make these devices is very tight, is very small. So it's a very difficult pixel, although it looks very simple. And actually, to make a CMOS or to develop a CMOS image sensor, you need an engineering team that is composed out of multiple disciplines. And the first discipline that I would like to mention to you is optical design of your pixels. You have to make sure that every available photon is finally landing in the right pixel. You have to take care about lenses, you have to take care about filters, reflections, and so on and so forth. A beautiful example is, for instance, the metal layers that you have on top of your pixels. Metal layers are not transparent for light, they are opaque. And crosstalk, you have to prevent that a particular photon is landing in your neighboring pixel. That is meant by crosstalk. Next to optical design, we are going to look into the semiconductor physics. You have to make sure that the generated electrons in your silicon are caught by the right pixel and that they also contribute to the output signal. And that actually with semiconductor physics, you have to focus on the photodiode design. You have to make sure that you have a complete charge transfer from your photodiode to this readout node where you convert your charge and a voltage. And you have to keep an eye on the leakage current. You have to make sure that the leakage current is as low as possible. Next, we have the analog circuit design. Do not forget the core of a digital imaging chip is still analog in nature. We have to deal with the noise. We have to deal with the noise of our buffer over here. And there is a worldwide known guru in analog design who wrote in his book, "Never use source follower." Well, that is exactly what we do. We do use source followers. Why? Because in that case, our buffer can be composed out of one single transistor. And space in the pixel itself is extremely, extremely important. So we limit ourselves for the buffer to one single transistor being a source follower. And we all know that has issues with noise, has issues with linearity and so on and so forth. But we have to deal with this. And another very interesting problem that is popping up with your analog circuit design are stable reference voltages, bias voltages, power and ground lines. If you look to the circuitry that we have available on the columns, so to say, they are spread out over centimeters from left to right on the chip. And you have to make sure that you have stable analog references, analog bias voltages from left to right over various centimeters across the chip. That is not so straightforward. Then finally, we are going to convert our signal from the analog domain into the digital domain. And for that reason, you need analog to digital converters. We have to take care about speed, power, linearity, and so on and so forth. And we can have a single A to D converter, although that seems to be a little bit old-fashioned. A single A to D converter on the chip. We can have a to D converter on every column, and then we have thousands of these A to D converters on the chip. But you can even have the A to D converter present in every pixel. And then we are talking about millions of ADCs on a single chip. So that changes the technology completely. Next to the mixed signal, we have digital circuit design. Digital circuit design is needed to drive to synchronize all the pixels, because you have to keep in mind that millions of pixels have to work together with the outside world. So you need a lot of control, timing, and driver circuitry. You need a lot of on-chip memory, but RAM as well as non-volatile memory. And sometimes, depending on the application, we also have a large part of the ISP, the image sensor, or the imager signal processing, or DSP, if you like, on chip as well. And that all in the circuit domain, of course, and the digital domain, of course. Fabrication technology, all these beautiful technologies, they need to be put on a piece of silicon. And for that, we need a fabrication technology that has a high yield, that has a low cost. But I mentioned already earlier that, for instance, a DRAM process is not capable of making high-performance CMOS images. Why? Because in a CMOS device, we need low VTs, we need pin photodiodes, we need a low leakage current, and these kind of things. And if we go to large devices, I mentioned already, devices of 20 by 20 centimeter, we need dedicated stitching technologies. And then if we look more to more recent developments, we go after backside illumination, bring the photons from the backside to increase the light sensitivity, and stacking, where we actually have 2 layers of silicon on top of each other, or actually 2, sometimes already 3 layers on top of each other. And you all need dedicated technology, all need dedicated processing steps to make these devices. And that's the reason why DRAM technology is not directly, not immediately compatible with CMOS image sensors. I mentioned to you that we have a constant drive to go to smaller pixels. I also said if you go to the smaller pixels, then actually what you see is that the performance is getting worse. If you do not change the technology, that statement is indeed correct, that your performance is getting worse. But if you look to what we have done over the years, we went to smaller pixels. But the performance of our devices, of our cameras, they were even improved. And that has to do with the fact that you have to improve the technology. You have to constantly work and further improve the technology. And a very interesting parameter to show you the evolution of the technology is, for instance, the leakage current, which is a very typical development, a very typical process optimization for CMOS image sensors. Horizontal axis, we have the year over here, as you can see again. And on the vertical axis, we have the leakage current, actually the leakage current density. It's expressed in amps per square centimeter. And this way, you get rid of the pixel size. And what you see actually is that also here, over the last decade, we came down, all the way down from very large values. But there seems to be a kind of a plateau over here that is being reached. And that plateau was already forecasted a long time ago by Mr. Slotboom in 1981. He said that the lowest level of the leakage current at that time in CCDs, but it's also valid, by the way, for CMOS devices, the lowest leakage current that you could reach will be around 1 picoamp per square centimeter at room temperature. He did this prediction based on the saturation current of bipolar junction transistors. So it doesn't always have to be Moore's law. From now on, we also talk about Slotboom's law, who is telling us what the lowest level of the leakage current is going to be. Yeah. I show you here a cross-section of what I call an old-school CMOS image sensor. If I remember well, this device is about 10 years old. You can recognize, if you go from the top and nicely follow how the photons come to the silicon, you can recognize over here the micro lenses. If you look carefully below the micro lenses, we do have the color filters. Over here, the dots, so to say, they are the metal layers, cross-section through the metal layers. And over here, we have the monocrystalline silicon. So the photons, they come nicely through the micro lens, they pass through the color filter, over here, so to say, through this tunnel of metal lines, and then finally generate an electron hole pair in the silicon. If you compare this with an advanced device that we have today, and actually that we have of that we see in mobile phones, then you see immediately what enormous progress the technology has made over the last decade. It's a backside illuminated device, I will explain immediately, and it is nicely stacked on top of the processing IC. So what do I mean by stacked? We have the image sensor with the top side over here. We have the processing device, the digital signal processor with the top side over here. And we nicely attach them to each other with former front side to front side. And then we bring the photons from the back side. So if I follow again the path of the photons, what you see here are the micro lenses. The spongy structures over here are the color filters. And then you reach the monocrystalline silicon, where the photons are converted into electron hole pairs. The thickness of the remaining silicon over here is just a handful of micrometer, 3-4 micrometer. Because it's turned upside down, you see here the metallization on the former front side. And here you make, by means of these bond pads, you make direct contact, bond pad contact to the processing die that is below the image sensor. I would like to draw your attention to actually 2 technology miracles, as I describe them, as I would like to describe them. And the first one is the alignment. Please keep in mind that we are working with wafers of 300 millimeter, 2 wafers of 300 millimeter, and they are stacked together in such a way that you have a beautiful alignment over here from your copper to copper bond pads. It's a self-aligned process, but look to the accuracy over here of the alignment. So we have 2 bond pads over here in contact with each other. The size of the bond pad, the width of the bond pad is 1.25 micrometer. And look to the accuracy over here of the alignment. This is in the nanometer range. That corresponds to the fact that if you would like to park your car with such a high accuracy, you have to go after an accuracy of 0.1 micrometer. This is really, really incredible how this can be achieved in this technology for the so-called hybrid bonding or stacked CMOS image sensors. And the second miracle that I would like to show you is the deep trench isolation. You see that deep trenches are being made through the monocrystalline silicon to define the pixels, or actually to help you to reduce the crosstalk. So photons penetrate into the silicon, and you see that this particular photon is coming into the silicon and tries to go to the neighboring pixel. Then by means of the deep trench, you create a kind of a mirror over here with total reflection, and you force the photon to stay into this particular pixel. Then the photon can generate an electron-hole pair, and then you have to collect that electron, but you see that electron is trying to escape to the neighboring pixel again. Well, in that particular case, also here, your deep trench is going to help you to keep this electron within the same pixel to prevent crosstalk. Optical crosstalk in the first place, electrical crosstalk in the second place. I have some numbers for these deep trenches, although the numbers that I show you do not belong to this picture over here. In this picture, we have pixels of a width of 0.8 micrometer. And what I show you here, the numbers for the DTI, for the deep trench isolation over here, is coming from a device with 0.7 micrometer pixel. The width of the deep trench isolation, the width is 84 nanometers. And for this 0.7 micrometer pixel device, they go 6.5 micrometer deep into the silicon. So that is an aspect ratio of depth over width of almost a factor of 70. And what is happening then, after the deep trenches are being created, the side walls of the trench is oxidized, and then the remaining gap is refilled by polycrystalline silicon or tungsten. And the remaining gap, as shown over here, the remaining width to fill this trench is only 53 nanometers. 53 nanometers. And a lot of people say, well, yes, micrometer and advanced technology and blah, blah, blah. But you do not realize what a kind of a technical achievement that this is, the deep trench isolation. And if you would like to get a better idea, then I challenge you actually to simulate a deep trench isolation this weekend in your garden. If you use a shovel of 25 centimeter in width, and you would do the same thing as what is done in the 0.7 micrometer pixel image sensor, if you would like to do the same thing with an aspect ratio of 70 or 69, you have to go 17 meter deep. The trench in your garden needs to have a depth of 17 meters. And if that's not enough, I also calculated the length of the DTI on the chip, and on the 44 megapixel chip with a 0.7 micrometer pixel size, they have in total 61.6 meter of deep trench isolation. Well, if you do the same thing in your garden, you have to make a trench 15,000 kilometers in length. So that is what is happening in the technology. That is what is happening in the creation of these deep trenches. And the deep trenches are really, really a key success factor in the technology and in the fabrication of the small pixels to prevent actually the crosstalk, as I mentioned to that. So I've been talking about how these devices are being made, a little bit, the hybrid bonding and also the deep trench isolation. Now we are going to take a look at the complete other side, at the output of the device. And actually, the title over here says, nobody is perfect. It starts already with the fact that our devices, our pixels, they sense one particular color, red or green or blue. While in the display, we need all three colors, RGB, in every pixel present. What I did is I added over here to a hypothetical output signal of an image sensor, I added temporal noise, I added spatial noise, leakage current, pixel defects, as well as column defects. I would not say that every image sensor is giving this type of signal, but every image sensor can have or will have noise, will have pixel defects, and sometimes even column defects, depending on the size of the devices. Nobody is perfect, but with a little bit of help of our friends, we can turn that ugly image into a beautiful image. And our friends in this case is the image sensor processing chip. So what is being done over here in the first place is that we reconstructed red, green, blue in every pixel. We call this also demosaicing. To actually cope with the spectrum of the light source, we go through an auto-white balancing. And then we need to find algorithms, dedicated algorithms for to correct the temporal noise, to correct for the spatial noise, leakage current, pixel defects, and column defects. And you see that at the end of the road, we have beautiful images generated by means of a image sensor with limitations in combination with a dedicated ISP. I would like to talk a little bit about the future. How do I see the future for our image sensors? And I would like to split this up in visual and the non-visual applications. And the first one is the visual. And strangely enough, I would like to tell you what I think is not going to be the future of imaging. We have seen recently, last decade, and also before that, but also recently, we have seen quite some announcements about image sensors, CMOS image sensors, that are being covered with a photoconducting or the photoconversion layer on top of it. And then you should think about amorphous silicon or germanium or photoconductors or quantum dots, you name it. There are various options out and various examples are being published. I think that for visual imaging, silicon is and will be unbeatable. So I think that all these alternative technologies, they will not make it for visual imaging, for sure not for consumer imaging. And why? Well, that's actually the answer is very simple, because our devices that we have today, they are coming close to perfection. Quantum efficiency is over 80%. Noise levels are down to 1 electron or even less than that. And the dynamic range that we have these days in our devices is over 80 dBs already. So there's not that much to gain anymore. Absolutely not. And what I think is going to happen in the near future is that the focus will shift from the image sensor to the signal processing part. Think about the stack technology that does allow us to combine an image sensor with the digital processing. Neural networks are popping up and they are going to replace the standard signal processing engines. And then finally, at the end of the road, I think that ultimately the pixels will become the first layer of the neural network. So the neural network, being the DSP, or part of the DSP, is going to integrate all together with the CMOS image sensor. That's what I think is going to be the future for visual imaging. Of course, if we talk on one sheet about visual imaging, we should talk about non-visible imaging as well. And to better define what I mean by non-visible imaging is the following. I show you here the spectrum. On the horizontal axis, we have the wavelength in micrometer. The part that is reserved for the visible spectrum, so to say, is very narrow. It's between 0.4 and 0.7 micrometer. But there's a very interesting region, a very interesting part of the spectrum, which is being known as the SWIR, the short wavelength infrared, for various applications. I will show you immediately on the next sheet which type of applications. And the SWIR is defined between 0.9 and 1.7 micrometer. There are other bands of interest, the middle wavelength infrared and the long wavelength infrared, but I will not talk about these applications of these parts of the spectrum yet. Now, if you look to what silicon is capable of doing, we see that the sensitivity of silicon is just going beyond 1 micrometer and then it's over. Silicon is becoming transparent for most of the wavelength in the SWIR bandwidth. And if you are interested in the SWIR bandwidth, then you have to go to other materials. And the other materials, I listed a few of them over here. Most popular over here are the InGaAs and germanium. In that case, you have to work with a foreign material on top of the silicon to convert the SWIR part of the spectrum to make actually your image sensor sensitive to these wavelengths. Why are we so interested in the SWIR part of the spectrum? Well, that part between 0.9 and 1.7 micrometer, if you operate in that part of the spectrum, you can work with very high power lasers, so to say, and without violating any eye safety rules. So the eye is less sensitive for this wavelength than for the short infrared. If you operate, for instance, a depth measurement in the SWIR band, there are particular segments in the spectrum where you have hardly any sunlight. So then it's very easy to operate these measurements, 3D measurements, distance measurements, also in sunlight conditions, because the sun does not emit particular photons in these particular wavelengths. The same is true for water. Transparency of water is depending very strongly on the wavelength, and there are parts in the SWIR spectrum that allow you to increase the transparency of water. Snow, for instance, then you can look through snow, for instance, you can look through fog, you can look through rain. And last but not least, around 1.55 micrometer, also blood is becoming transparent. So if you work at this wavelength for medical applications, that can be of large interest. That can open new applications for medical diagnosis, for instance. Another thing is that our stacking technology is expanding from wafer to wafer, from wafer to wafer to die to wafer, and finally even from die to die. That does allow us to actually make the combination of these foreign materials for non-visible imaging, these foreign materials with a silicon readout IC, a so-called ROIC. And actually the combination is going then with the advanced technology, is opening new and lower cost options for distance measurement, distance characterization. Think about LiDAR and SPAT applications, as well as multispectral imaging. I have one sheet, or actually two sheets, about privacy. Very hot topic these days. You have to keep in mind that cameras are being present these days all over the place, even in the smallest room of the house, so to say. And these cameras, they track where we go, they track what we eat, they track what we buy, and so on and so forth. And you can say that Big Brother is watching us, and that Big Brother can interfere at any given time. Moreover, we are making extensive use of image-driven applications. So we, consumers, we are uploading billions and billions of images and videos on a daily basis. And the combination of the output of these cameras, all these billions of images that are available on the web, together with artificial intelligence, they can not only detect people, but they can also recognize people. And that is going to be extremely dangerous. Also in combination with the fact that the definition of privacy is different in various parts of the world. So what we also see is that people are willing to give up part of their privacy in return for security or safety. But we consumers should realize that once we gave away to our government, we will never get it back. So here there's a task for the ISSCC community, so to say, and the task is called responsible innovation. We should use the advances of the technology, but we should try to avoid the dangers of the technology. And there's a beautiful example that I can list over here in relation to cameras. That is the use of a camera as a people counter. There is no need to store, if you need to count people, there's no need to store images. Because images, once they are stored, they can only be misused. And if that is not going to happen today, it might happen tomorrow, for instance, because tomorrow the technology that we have available tomorrow will be more advanced than the technology that we have today. Now, there was a nice, interesting presentation of an event based on neuromorphic camera. With such a camera, you can easily, CMOS device, CMOS based, you can easily detect people, but you cannot recognize people. And for a people counter, so to say, that is exactly what you need. That is what is being known as responsible innovation. And then I come already to the conclusion. And I would like to start, or I would like to repeat over here the title of my talk. There's more to the picture than meets the eye. Taking a picture requires more than just a trigger to our sensor, a trigger that is coming from the red button. Keep in mind that many artifacts will contaminate the raw image data. And then you should think about noise, defects, false colors, lens issues, and so on and so forth. But together with powerful processors in combination with cheap memory, the output signals of our image sensors, although image sensors are not perfect, the output of our image sensor can be turned in almost perfect images. And the subtitle, remember, was, and in the future it will only become more so. Deep trench isolation and stacking technology, they will improve towards smaller dimensions than what we have these days already. Processor architectures are moving towards artificial intelligent engines. And for sure, we are going to use, or we are going to expand the application area to the so-called SWIR part of the spectrum. And for sure, this will this will open up for new applications, and this will open up to new horizons. Thank you very much for staying with me till the end of my talk. Bye-bye.